So in the last class, we have discussed about the definition of algorithm, and then we also discussed about the different algorithm types. Those are brute force, greedy algorithm, recursive method, backtracking, dynamic programming, divide and conquer. So there are different algorithm techniques also. We have also discussed the definition of algorithm. And along with this, we have also discussed how to measure that which algorithm is best for a particular problem. Because we have seen for a particular problem, we can write many solutions. Such as in the last class, we have discussed prime number, whether a given number is prime or not. To select or to check whether a given number is prime or not, we have seen we can write 3 to 4 types of different solutions. And among those solutions, which one is best, that will be decided on the basis of 2 different parameters. And those parameters are, one is time complexity, okay, and another parameter is space complexity. And I have also given you some idea why time complexity is more important than the space complexity. Because time is still a limitation, but space nowadays is not that much limitation, because we can use a huge amount of RAM size, but still the total time is not changed. We have modified the speed of the processor, but still the time is the most important factor. And we have also discussed how time and space, these two things or these two parameters, having some trade-off between them. For example, we have seen that how to transfer from one particular city to another particular city. There are different possible ways to transfer from one particular city to another particular city. But among those different solutions, we have to consider the best one. If we consider with respect to time, then we have to choose a different solution. If we consider with respect to, say, cost, we will choose another solution. So, finally, we can say that time complexity is more important than space complexity. But if you developed any new algorithm for a particular problem, then you must give both time complexity and space complexity. And it is very rare that your algorithm can be solved in both with less time and less space. Okay. So now today we will try to understand how to calculate the time complexity for a particular problem or particular algorithm. Now, if we say that for a particular problem, or sorry, a particular solution, how to calculate the time complexity, let us write one simple, simple code, C code, to calculate the total time. Now see, time complexity and total time required, these two things are different. Remember this, time complexity calculation and total time required for a particular solution or algorithm is different. Time complexity, it should be always in terms of some mathematics. We will solve it in terms of some mathematical conception. But total time is the exact time, either in second or millisecond, that is taken by the system to solve that particular problem. Okay, let us write one simple example how to calculate the total time required to run a program. Okay, now suppose I have declared some variable here, say a and say x. Okay, then I have written a printf statement, say enter value. Okay, then I have used one scanf statement to take input from the user, say x Then suppose I have used one for loop to perform some particular operation. So let us write it like this: I less than say x, then I plus plus. Then inside this I, suppose I am writing a equal to a plus I, and then finally suppose I am printing the exact value of this a, that is %d a. So this is a very simple algorithm, simple problem, and we should initialize. If we initialized a equal to 0 in the first statement, then we can say that this is a program for sum of n natural numbers, you can say n natural numbers. So there's a simple problem. The sum of n natural number means it will give you a equal to 0 plus 1 plus 2 plus like this up to say if I use equal to, then up to x. Okay, so this is a simple program, and if we want to calculate the total time required to complete this code, then you must have to understand how many statements are there. This is the first thing. How many statements I have written are there. This is very important. See, this end of semicolon means one particular statement. Okay, one semicolon means one particular statement. Now, if I consider that to run or execute one statement, we require suppose t millisecond of time. Then if we know how many statements are there, then we can easily calculate the total time required by the compiler to run this particular code. Okay, now this is very simple calculation. So how many statements are there? So this is statement number 1, this is statement number 2, this is statement number 3, then this is 4. Then how for loop will run? First initialize, then it will move for condition checking. So this is 5. Then it will go for this one 6. Then it will go for this one 7. Again it will go for this one 8. Then this one 9. Then this one 10. And in this way it will continue the operation until I becomes greater than x. When I becomes greater than x, it will break. It will stop. Okay. So now see, inside this for loop, the number of statements is basically depends on a particular value or variable. Inside this for loop, the number of statements is not independent, it is dependent on a particular value x. Instead of writing x, if I write here directly say 10, then we can say it will run how many times. But if I write here x, then it depends on a particular value x. If x is a small value, the number of statement will be less. If small is a high value, the number of statement will be high. And then finally, this is another statement. So if all together there are, suppose there are capital X number of statements, then we can easily calculate that x into t is the total time required to execute this program. But see, here we have considered taken one assumption that all the statements are having required equal time. We have considered this assumption that all this single statement will take same time, but this is not happening inside the compiler, because for a scanf it will take more time than this declaration or I equal to 0 initialization. This printf will take more time than this I equal to 0 or I less than equal to x. Now see, this I equal to 0 will take less time than this I less than equal to x. Now you can easily understand why this one will take more time than this. Why? Because here we have to call the ALU. ALU actually perform this operation. But in this operation, the time is, since this is only an initialization, so there is no require of this ALU. Okay, so that's why the time is dependence on each and every statement. If we change the time for each and every statement according to its performance, then the total time is a different value from this. But if we consider that for this particular program, each and every statement is equal. It means they are taking, or our compiler is taking same time to execute this statement. Then we can easily calculate the total time required. Okay, but see, this is not the way through which we can represent the time complexity of an algorithm. Why? See, this T, the time required to solve a particular statement, to execute a particular statement, this is itself machine dependent. This is itself machine dependent. Why this is itself machine dependent? Because it depends on the processor speed. Clear? So that's why this value is machine dependent. It means if I run this algorithm in a, say, Pentium 2 or Pentium 3 processor, then it will take more time than if I run it in a Core 2 Duo processor, because the speed is varying. So it means this total time required by an algorithm or a program to execute is not a exact measure to compare the betterment or which one is the best. Clear? If I calculate total time required for a particular algorithm, then it is not, we cannot say exactly whether it is the best solution or not. Because if I run one algorithm in a faster processor, then it will take less time. If I run same code in a slower processor, it will take more time. So from that, we cannot compare which one is best. Okay, that's why we have some mathematical formulation or representation for the time complexity. Okay, and this mathematical representation or this mathematical calculation is called asymptotic notation. Okay, this mathematical representation of time complexity actually represented by some mathematical formulation which is called asymptotic notation. Actually, in asymptotic notation, what we try to represent some bounds with the help of graph and functions. Okay, so what we try to implement in this asymptotic notation, we try to implement how my algorithm will change, or how my algorithm will depend on different input and output. Now, if we think that that the runtime of an algorithm is a input to a function. Suppose I have a function f, and the input to the function is say x and y. These two are the inputs. What is the meaning of x? The meaning of x is number of inputs in the algorithm, and y is number of output or output values in the algorithm. So here we are trying to give input the time runtime as an input to the function, and then it will give us some value, and then it will give us some value, and that value will measure the time complexity of the algorithm. It means to measure the time complexity, what we are giving inside a function, we are giving number of input and output, how these two are related. And based on this input and output, we can calculate a graph. Suppose I have two variables. If I give, so this is one value and this is another value. If I draw a graph on the basis of this, then we will get some graphical structure like this. Okay. And then based on this graphical structure, we can calculate two different bounds. Okay. Bounds means the limitation. Okay. One is called the upper bound and another is called the lower bound. Okay. So bound is what? Bounds are functions that we use to compare against a, suppose, a given algorithm function. So I have a given algorithm function. If I want to compare it, then we will use some bounds. And what is the meaning of bounds? Again, it is some, it means some graphical representation, means from this input and output value, if we draw a graph, then it will give us some mathematical representation of the algorithm. Okay, let us take one simple example. Suppose let us take some example, like suppose if we if you know the bubble sort, then the bubble sort algorithm will require n into n minus 1 by 2. So it will require this amount of time, or you can say comparison. Okay. Now, so this is n square by 2 minus n by 2. Now, if we draw this in a graph, so in this axis, the value of n, and in this axis, so if this is a function n, then in this axis, the value of function n. If we draw the graph, so these are the values, suppose these are the n1, 2, 3, like this. So if we say if n equal to 1, say n equal to 0 in this point, n equal to 0 in this point, it will be 0. Then n equal to 1 means 1 by 2, 1 by 2. So again it is 0. Then n equal to 2, it becomes 2 square 2. So it becomes 1. So here in n equal to 3, it is 3 into 2 means 3. So if we draw like this, the picture will be like this. The graph will be like this, Okay. So now from this representation, we can understand. So this is the actual graphical representation of the time complexity of this bubble sort. But finally, we will bound them. Finally, we will represent them with some bound. And there is one upper bound and lower bound. So these two, upper bound and lower bound, are the two different representation of algorithm. Okay. Now the upper bound representation. So let us now going to the definition of this upper bound and lower bound. So the upper bound of any algorithm, is represented by big O notation, So this is the asymptotic notation, which is used to represent the big O of a or upper bound of an algorithm. So if suppose, so this is our Fn. Suppose Fn is a function, and we are going to represent the time complexity of this function as O of Gn, then it should satisfy this particular relation. It should satisfy the particular relation. The relation is like this: Fn must be greater than equal to 0, but less than equal to C into Gn. Okay, where C is a positive constant, C is a positive constant. Okay, and similarly, there must be some value for which n is greater than equal to n of 0. So if we draw this type of graph, it will show like this. It will show like this. Suppose this is the time complexity of that particular function. So suppose this is fn, then the gn will be like this. Suppose the gn, c into gn will be like this, c into gn. Okay, so after this value, so this is our n0 value. So after this value, see, before this n0 value, this fn is this black curve. Fn is greater than c into gn. But after this particular n0 value, the graph c into gn always greater than this. And if this is satisfied, then we can say that fn is equal to order of gn. And this is the upper bound of the algorithm. Okay. Now, similarly, we can represent the lower bound of an algorithm, which is called the lower bound, or sometimes which is called omega notation, lower bound, which is also called omega notation. This is big O notation. This is omega notation. So in this omega notation, it will be represented. The definition is a little bit different. How? Since it is lower bound, so fn can be represented like this, omega of gn. And in this case, since it is lower bound, so in this case, c into gn will be less than fn. So your graph will be like this. So if this is your fn function, then your gn function will be like this. So after this particular value, n0, c into gn is always less than the fn. Okay, and this will represent the lower bound. This will represent the lower bound of the algorithm. Okay. Similarly, there is another type of asymptotic notation which is called theta, notation, represented like this, theta, and we can say that fn is equal to theta of gn. Okay, and this will give you a bound which is called you can say this is exact bound. Exact bound means it will give you both lower and upper. Both. It will give you both lower and upper bounds. That's why it is sometimes called exact bound. Okay, so it means your graph will be like this. There will be two values. One is like this. Another graph will be like this. This is C1 into Gn, and this one C2 into Gn. So your equation will be like this. The equation 0 less than equal to C1 into this one C2. So C2 into Gn, which is less than equal to Fn, and which is as less than equal to C1 into Gn. So this will be a representation of theta notation, which will provide you the exact bound of both upper and lower bound. But remember, among these three types of representation, theta, omega, or big O, the big O notation is the most important. Okay. Now we will discuss why big O notation is important. Now before that, we have to understand another thing, that for a particular algorithm, when we are giving some input, that input is, you can say, the input sequence. The input sequence is very important. Very important. Why this input sequence is very important? Now suppose we want to calculate the maximum or minimum from an unsorted array. Okay. Now suppose I want to select the maximum or minimum from an unsorted array of say n elements. Okay. Now, if it is unsorted, then it is very difficult to calculate, or it is very difficult to say that we can perform the operation within less than n comparison. If there are suppose n elements in an array and I want to calculate how many comparisons, so how we will perform this operation, max or min? We know we will choose the first number as the max or min, and then I will compare this with the rest of the array element. Clear? And if any element is maximum or minimum than the selected element, then that becomes max or min. So see, in this particular problem, it is not possible to say beforehand that which one is the max or min until you compare your element with all the elements. So this is purely brute force algorithm. There is no other solution. You have to perform this by comparing each and every element. Okay, but suppose in a sorting, suppose your array is already in sorted order like this 1, 2, 3, 4, and you are asked to perform a sorting algorithm of ascending order. Then see, this will take minimum time. Similarly, if you are asked to perform ascending order for an array where elements are in reverse order, then it will take the maximum time. It means for a particular element, the input sequence is very important. Now we can say that this particular input sequence can have many permutations. But among those permutation, the permutation or the sequence which will minimize the time, minimize the runtime, that is called the best solution or best case. Clear? Among different sequence of permutations, the sequence which will take minimum runtime or minimize the runtime, that will be called the best case. Similarly, you can understand what is the meaning of the reverse, or which will take the maximum time, that will be called the worst case. So for any particular algorithm, if you want to calculate the time complexity, then you must consider the worst case. And in case of worst case, what you will consider? You will consider the upper bound. Why? This upper bound is the minimum value. See what is the meaning of upper bound. Suppose this is one car. Say this is n square. So what I am telling you in the BIGO notation, it is telling that the value of Fn, must be less than equal to C into Gn. Okay. Now see, suppose this is n square. This is n square minus 1. So obviously this is less than n square. So this n square is the Gn. Okay. And this is the Fn. Clear? Now this n square minus 1 is also less than n cube, also less than n to the power 4, also less than n to the power infinity. Logic clear? I am telling that Fn will be less than C into Gn. Now n square minus 1, if the function is n square minus 1, obviously this is less than n square. Again, it is also less than n cube. So now among these values, it will take the minimum one. This upper bound or BIGO notation will take the minimum one. So in worst case, minimum is the standard. So if I am able to minimize my time complexity, then that lower value, this minimum value, then I can say that my algorithm is best. Is it clear? I hope not clear. So what is the use of worst case? Because worst case is the measure of an algorithm when the data sequence or input sequence in a totally in the bad possible situation. The input is in the bad possible situation. Suppose I'm performing searching. So in case of searching, if my search element at the 0th position in the array, if my search element is in the 0th position, then I will say this is the best case. Why? Because only one comparison is required to search my particular element. But if my element is at the end, then I will say this is the worst case because it will take the maximum time. So what is best case? If I for a particular data sequence, the runtime of the algorithm is minimum, then it will be called best case. And if the runtime is maximum, then it will call the worst case. Now see, in why we always try to consider worst case upper bound. See, in case of upper bound, what we are representing? We are representing fn, which is a actual function, is less than this time complexity. Okay. Now, if the function is n square minus 1, then it is obvious that it is less than n square. Correct? Then we can also say that this is also less than n cube. It is also less than n to the power 4. We can, but among this n square, n cube, n4, n to the power infinity, we are only choosing the minimum value. It means in worst case, this is the minimum time required. For worst case, this is the minimum time required for an algorithm. So if I propose another algorithm, which will take in worst case less than the minimum time, less than this, then I will say that this algorithm is the best one. Is it clear or not? Please. In big O notation, suppose this is the car. This is the lower bound. This is C into Gn. And this is the worst case lower bound. This is the worst case lower bound. Sorry, worst case upper bound. Clear? Now, so upper bound means the worst case minimum time. So if I am able to give some new algorithm which will take less than this, but greater than the actual function, this is the actual function, but this is my new algorithm, say my new algorithm is X, then I will say that my algorithm is better than the existing algorithm. So that's why when we consider time complexity, we always try to give the worst case upper bound. And how to represent upper bound? We can represent upper bound with respect to, say, big O. That's why big O is that much important. We always try to represent the time complexity with respect to big O notation. Is it clear or not? Please tell me. If any query, you can ask.
Yes, sir, clear, sir.
Okay. Now, so there is only 1 minute left. So after 5-minute break, we will meet again, and I will discuss how to calculate the time complexity. See, all this definition is not required to calculate your time complexity. These are only for theoretical representation, and some question may come from this part, that what is the meaning of big O notation, what is the meaning of omega notation. So that's why I am giving you the definition or mathematical representation of these formulas or of this notation. But the actual, how we will calculate the actual time complexity, if you see in book, it will always give time complexity order of n square, order of n log n, order of n, like this form. And here we always use only the big O notation. And why only big O notation is used, I have already discussed. So I hope it is clear now. Now, in the next part of this class, I will discuss how to measure actually from a code or from an algorithm, how to calculate the time complexity. Okay, so we will meet again after 5 minutes break.